A binary compound of oxygen with another element is called an oxide. On the basis of their oxygen content, oxides can be broadly classified into simple oxides and mixed oxides. Simple oxides are oxides that contain just as much oxygen as permitted by the normal valency of its metal. Examples of simple oxides are magnesium oxide and aluminium oxide. Mixed oxides are oxides that are made up of two simpler oxides. For example, red lead, Pb3O4, is a mixed oxide of lead monoxide, PbO, and lead dioxide, PbO2. Similarly, ferroso-ferric oxide, Fe3O4, is a mixed oxide of ferrous oxide, FeO, and ferric oxide, Fe2O3. On the basis of their chemical behavior, simple oxides can be further classified into acidic oxides, basic oxides, neutral oxides, and amphoteric oxides. An oxide that combines with water to give an acid is termed as an acidic oxide. Generally, oxides of non-metals, such as carbon dioxide, sulfur dioxide, sulfur trioxide, phosphorus pentoxide, dichlorine heptoxide, and dinitrogen pentoxide, or metallic oxides of high oxidation states, such as manganese heptoxide, chromium trioxide, and vanadium pentoxide, are acidic in nature. For example, sulfur dioxide dissolves in water to give sulfurous acid. Similarly, chromic anhydride combines with water to give chromic acid. An oxide that gives a base with water is known as a basic oxide. In general, oxides of most metals, such as sodium oxide, calcium oxide, barium oxide, are basic in nature. For example, calcium oxide combines with water to give calcium hydroxide, which is a base. A few metallic oxides exhibit dual behavior. Such oxides are known as amphoteric oxides. They react with acids as well as alkalis. For example, zinc oxide behaves as an acidic oxide when treated with concentrated sodium hydroxide. and as a basic oxide when treated with hydrochloric acid. Similarly, aluminium oxide reacts with acids as well as alkalis, as shown here. Neutral oxides. These oxides do not show any tendency to form sols when treated with acids or bases. For example, carbon monoxide and nitrous oxide are neutral oxides. Ozone is an unstable triatomic allotropic form of oxygen. It is present in the atmosphere for about 20 kilometers above sea level. It is formed from the oxygen present there under the influence of ultraviolet light from the sun. Ozone is of vital importance in protecting the Earth's surface from excessive exposure to ultraviolet radiations. However, the use of chlorofluorocarbons in aerosols and refrigerators and their subsequent release into the atmosphere is blamed for making holes in the ozone layer over the Arctic and Antarctic regions. It is feared that this will allow excessive UV light to reach the Earth, which can cause skin cancer in humans. Studies have shown that oxides of nitrogen, particularly nitric oxide, combine rapidly with ozone to form nitrogen dioxide and oxygen. Thus, the oxides of nitrogen released from the exhaust systems of supersonic jet aeroplanes slowly deplete the ozone layer. Let's now look at the preparation of ozone. Ozone is prepared by passing a silent electric discharge through dry, pure and cold oxygen in a special apparatus called the ozonizer. Concentrations of up to 10% of ozone are obtained in this way. The formation of ozone is an endothermic reaction. It must be carried out at high temperature. Hence, it is prepared by means of silent electric discharge. Otherwise, sparking would generate heat and decompose ozone. Higher concentrations or pure ozone can be obtained by fractional liquefaction of an oxygen-ozone mixture. Let's look at the physical properties of ozone. Ozone is a pale blue gas with a characteristic fishy smell. It condenses at -120 degrees centigrade as a dark blue liquid. This, on further cooling, gets solidified to violet-black crystals. Small concentrations of ozone are harmless. However, when the concentration rises above 100 parts per million, breathing becomes uncomfortable and causes headache and nausea. Ozone is thermodynamically unstable and decomposes to oxygen. The decomposition is exothermic and is catalyzed by many materials. Hence, high concentrations of ozone are dangerously explosive. Let's look at the oxidizing action of ozone. Due to the ease with which it liberates atoms of nascent oxygen, ozone acts as a powerful oxidizing agent. second only to fluorine. It reacts much more readily than dioxygen. For example, it oxidizes lead sulfide to lead sulfate, nitrogen dioxide to dinitrogen pentoxide, and iodide ions to iodine. The amount of ozone in a gas mixture may be determined quantitatively by passing the mixture through a potassium iodide solution buffered with a borate buffer. The iodine that is liberated in the reaction is titrated with a standard sodium thiosulfate solution. The amount of iodine consumed in this reaction gives the amount of ozone present in the gas mixture. Let's study the structure of ozone. The ozone molecule is symmetrical and bent with a bond angle of about 117 degrees. The length of the two oxygen-oxygen bonds in the ozone molecule is the same, that is, 128 picometers. This bond length is intermediate between a single bond and a double bond. Ozone is, therefore, considered a resonance hybrid of the canonical forms shown here. Let's look at some important uses of ozone. Ozone is used as a germicide. Ozone is also used as a disinfectant. For example, it is used to purify drinking water, since it destroys bacteria and viruses. Since it decomposes readily to give nascent oxygen, it is used as a mild bleaching agent for bleaching oils, ivory, starch, flour, wax, and delicate fabrics. It is used in the manufacture of potassium permanganate from potassium manganate. It is also used in the manufacture of artificial silk and synthetic camphor. Sulfur has more allotropic forms than any other element. The two common crystalline forms are alpha or rhombic sulfur and beta or monoclinic sulfur. Rhombic sulfur is stable at room temperature, while monoclinic sulfur is stable above 369 Kelvin. These two forms change reversibly with slow heating or slow cooling. Rhombic or alpha sulfur occurs naturally as large yellow crystals in volcanic areas. Crystals of rhombic sulfur are formed by evaporating a solution of rolled sulfur in carbon disulfide. It has a melting point of 385.8 Kelvin and a specific gravity of 2.06. It is insoluble in water, but readily soluble in carbon disulfide. Monoclinic, prismatic, or beta sulfur is prepared by melting sulfur in a dish and cooling it till a crust is formed. Two holes are made in the crust and the remaining liquid is poured out. On removing the crust, colorless needle-shaped crystals of beta sulfur are formed. It is soluble in carbon disulfide. It has a melting point of 393 Kelvin and a specific gravity of 1.98. Monoclinic sulfur is stable above 369 Kelvin. Below this temperature, it turns into alpha sulfur. Alpha sulfur, on the other hand, is stable below 369 Kelvin and turns into beta sulfur above this temperature. At 369 Kelvin, both the forms are stable. The temperature at which the two forms are stable is called transition temperature, and the two varieties are called enantiotropic substances. Both these allotropic forms contain puckered S8 rings with a crown conformation and differ only in the overall packing of the rings in the crystal. In each ring, the atoms lie in two parallel planes, with the angles between the bonds all being 107 degrees and the bond lengths being 204 picometers. Several other rings, S7, S9, S10, S11, S12, S18 and S20 have been synthesized in the last 2 decades. In all of these ring compounds, the SS distance is 204 picometers. In cyclo S6, the ring adopts the chair form. The structure and the molecular dimensions are illustrated in the image here. Sulfur melts to form a mobile liquid. As the temperature is raised, the color darkens. The S8 rings break at 433 Kelvin. Sudden cooling of this liquid in water gives plastic sulfur or gamma sulfur. The vapor at 473 Kelvin consists mostly of S8 rings, but contains 1 to 2% of S2 molecules. At 1000 Kelvin, the gas mainly consists of S2 molecules. Like oxygen, the S2 molecule contains 2 unpaired electrons in the antibonding pi star orbitals, and hence exhibits paramagnetism like it. Let us begin with the methods to prepare sulfur dioxide gas. Sulfur dioxide may be prepared in the laboratory by the action of dilute sulfuric acid on sulfides. For example, sodium sulfide on treatment with dilute sulfuric acid gives sulfur dioxide as shown in the equation here. Industrially, large volumes of sulfur dioxide are prepared by roasting a sulfide ore, such as iron sulfide. After drying, the gas is liquefied under 25 atmospheres pressure and stored in steel cylinders. Sulfur dioxide is also obtained on a large scale by burning sulfur in air. In this reaction, about 6 to 8% of sulfur is simultaneously oxidized to sulfur trioxide. Let's now study the physical properties of sulfur dioxide. Sulfur dioxide is a colorless gas with a pungent smell of burning sulfur. Sulfur dioxide levels above 5 parts per million are poisonous. It is one of the easiest gases to liquefy since it condenses at room temperature under a pressure of 2 atmospheres. Let's now look at the chemical properties of sulfur dioxide gas. It is an acidic oxide that is highly soluble in water. It dissolves in water to give sulfurous acid. It reacts readily with sodium hydroxide solution and forms sodium sulfite. If more sulfur dioxide is passed into this solution, sodium hydrogen sulfite is formed. the sulfur atom in a sulfur dioxide molecule is tetravalent. Hence, it can extend its covalency to 6 by directly combining with elements like oxygen and chlorine to form the corresponding addition compounds. For example, it reacts with chlorine in the presence of charcoal as a catalyst to give sulfuryl chloride, SO2Cl2. Similarly, in the presence of vanadium pentoxide as a catalyst, it gives sulfur trioxide. In the presence of moisture, it can liberate nascent hydrogen and thus act as a reducing agent. For example, it reduces ferric salts to ferrous salts and halogens to halogen acids. Similarly, it decolorizes acidified potassium permanganate solution, turns a filter paper moistened with acidified potassium dichromate solution green and starch iodate paper blue. Note that these reactions are used as identifying tests for sulfur dioxide gas in the laboratory. The structure of sulfur dioxide is shown here. It is angular in shape with an OSO bond angle of 119.5 degrees. Note that although sulfur dioxide has two different types of pi bonds, that is, p-pi, p-pi and d-pi, p-pi, the two sulfur-oxygen bond lengths are equal. This indicates that sulfur dioxide is a resonance hybrid of two canonical forms as shown here. Let's look at the uses of sulfur dioxide gas. Sulfur dioxide is used in the manufacture of industrial chemicals like sulfuric acid, sodium hydrogen sulfide, and calcium hydrogen sulfide. It is used to refine sugar and petroleum. It is used to bleach delicate materials like wool and silk. It is used as a disinfectant for killing germs, fungi, and certain molds. It is used as an anti-chlor for removing excess chlorine from a fabric after bleaching. Liquid sulfur dioxide is used as a solvent to dissolve a number of organic and inorganic compounds. Sulfur forms a large number of oxo acids. Many of these do not exist as free acids, but are known as anions and salts. Oxo acids of sulfur, depending on their structural similarities, are divided into 4 series. They are sulfurous acid series, sulfuric acid series, thionic acid series, peroxo acid series. Oxo acids with SS linkages are called thioacids, while those with peroxo linkages are called peroxo acids. The table here shows the names, structures, and oxidation states of sulfur in its various oxo acids. As you can see, sulfurous acid, di- or pyrosulfurous acid, and dithionic acid are categorized under the sulfurous acid series. Sulfuric acid, thiosulfuric acid, and di- or pyrosulfuric acid are grouped under the sulfuric acid series. The thionic acid series includes dithionic acid and polythionic acid. while the peroxo acid series includes peroxomonosulfuric acid and peroxodisulfuric acid. Among these oxo acids, sulfuric acid is the most important acid used in the chemical industry. It is manufactured by the contact process. The contact process involves 3 steps. The first step is the production of sulfur dioxide. This can be made by burning sulfur or sulfide ores such as iron pyrites in excess of air. The second step is the formation of sulfur trioxide. Sulfur dioxide is oxidized to sulfur trioxide with atmospheric oxygen in the presence of vanadium pentoxide as catalyst. The third step is the conversion of sulfur trioxide into sulfuric acid. The sulfur trioxide formed in the second step is dissolved in 98% sulfuric acid to give pyrosulfuric acid or oleum. Oleum is then diluted with water to give sulfuric acid of the desired concentration. The plant used for the contact process is shown here. The plant includes pyrites burners or sulfur burners, dust precipitator, washing and cooling tower, drying tower, arsenic purifier, preheater, catalytic converter and absorption tower. Let's briefly discuss the different stages involved in the manufacture of sulfuric acid by this process. The sulfur or iron pyrites are burned in the sulfur burner to produce sulfur dioxide. The impure sulfur dioxide and oxygen gases from the sulfur burner are passed into the dusting tower where the dust particles are removed by settling down. The purified gases are now passed into the washing and cooling tower. Here, the gases are cooled and washed. The moist gases from this tower are passed into the drying tower. The gases are dried by a spray of concentrated sulfuric acid. The dry gaseous mixture from the tower is then passed through the arsenic purifier. The main impurity in the gases, arsenic oxide, is removed here. The pure gases are passed through a preheater and heated to about 673 to 723 Kelvin. Gases are then led into the catalytic converter. Here, in the presence of vanadium pentoxide as catalyst, sulfur dioxide and oxygen combine to form sulfur trioxide. The sulfur trioxide is then led into the absorption tower. In the absorption tower, sulfur trioxide is absorbed in concentrated sulfuric acid to form oleum. The oleum is diluted with water to get the acid at the required concentration. The key step in the manufacture of sulfuric acid is the catalytic oxidation of sulfur dioxide to sulfur trioxide with atmospheric oxygen. The forward reaction is exothermic and is favored by a low temperature. Since there is a decrease in the number of moles of gas, the process is favored by a high pressure. Hence, low temperature and high pressure are the favorable conditions for maximum yield. However, the temperature should not be too low, as the reaction would then become slow. In practice, the reaction is carried out at a pressure of 2 atmospheres and a temperature of 720 Kelvin. The sulfuric acid obtained by this process is 96 to 98% pure. Let's now look at the physical properties of sulfuric acid. Sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 Kelvin. It has a boiling point of 611 Kelvin. The high boiling point and viscous nature is due to hydrogen bonding, because of which a number of simple molecules bind together to form a cluster. Concentrated sulfuric acid has a strong affinity for water. A large amount of heat is produced when the acid is mixed with water. The temperature may rise to as high as 393 Kelvin. Hence, the acid is always diluted by adding it to water slowly with constant stirring. Remember, never add water to sulfuric acid. The evolution of heat is due to the formation of hydrates such as H2SO4, H2O, H2SO4, 2H2O, and H2SO4, 4H2O. Let's now study the chemical properties of sulfuric acid. The chemical reactions of sulfuric acid are due to its low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. Sulfuric acid is a strong dibasic acid. In an aqueous solution, it ionizes in 2 steps, as shown here. Note that the value of dissociation constant, Ka1, for the first step is very large as compared to the second step. The larger value of Ka1 indicates the greater extent of ionization of H2SO4 into H+ and HSO4-, which in turn indicates the greater acidic strength of the acid. The acid neutralizes alkalis and forms 2 series of salts, bisulfates and sulfates. For example, concentrated sulfuric acid reacts with sodium hydroxide and forms sodium bisulfate and sodium sulfate, as shown in the equations here. Sulfuric acid, being less volatile, is used in the manufacture of more volatile acids from their corresponding salts. For example, concentrated sulfuric acid liberates hydrogen fluoride from calcium fluoride, and hydrogen chloride from sodium chloride. Concentrated sulfuric acid is a powerful dehydrating agent. The dehydrating property is used in drying many wet gases that do not react with the acid. For example, gases like chlorine, sulfur dioxide, and hydrochloric acid are dried by passing them through sulfuric acid. Sulfuric acid also removes water from organic compounds like carbohydrates. For example, it chars sugarcane, glucose, and starch to carbon. Hot concentrated sulfuric acid is a good oxidizing agent. It oxidizes both metals and non-metals and itself gets reduced to sulfur dioxide. For example, hot concentrated sulfuric acid oxidizes copper to copper sulfate and gets reduced to sulfur dioxide. Similarly, it oxidizes non-metallic carbon to carbon dioxide and itself gets reduced to sulfur dioxide. Lastly, let's look at the important uses of sulfuric acid. Sulfuric acid, because of its wide applications, is referred as the king of chemicals. It is used in the manufacture of fertilizers like ammonium sulfate and superphosphate, dyes, pigments, and paints. Explosives such as TNT. Other important chemicals like hydrochloric acid, nitric acid, phosphoric acid, and sodium carbonate. It is used in the refining of petroleum. Sulfuric acid is also used as a pickling agent. Pickling is an industrial process for removing layers of basic oxides from metals like iron and copper before electroplating, enameling, soldering, and galvanizing. As a laboratory agent and a dehydrating and oxidizing agent,